Hi, I am Ben-Yaakov. This presentation is entitled High Frequency Power Inductor Design. Let me start off with a disclaimer stating that this design that I'm going to show does not include safety issues, so one should not attempt to use any of the designs according to the outline procedure given here in actual circuits unless being first approved by a relevant professional. Now, we are talking about power inductors. Now, the purpose of a power inductor is to store energy. We're talking about high-frequency power inductors that are used in DC-DC converters, switch-mode power supplies, in general in power electronics, and in some other areas. Now, there is a major difference between an inductor and a transformer, although from outside they may look the same, especially since some inductors may have multiple windings. That is, there might be another winding here, and so it sort of looks like a transformer, but inductors are not a transformer. The difference being that a transformer is transparent to the energy passing through it. That is, energy is coming one way and then coming out the other way. No energy is stored except for some energy required for magnetization of the core. The story is different in inductors. There is no energy coming out. The energy is stored into inductor. It's stored in a magnetic field of the core and then could be released to some other source, to a load, and whatever the application requires. Now, in order to maximize or optimize a power inductor, we normally use a ferromagnetic core. That is, the windings are put on a ferromagnetic core which has a high permeability. Permeability is defined, total permeability, as the initial permeability or vacuum permeability or air permeability times the relative permeability of a specific material. For air, it will be 1. Now, the advantage of the ferrite, or in general ferromagnetic cores, is that they do have a fairly high relative permeability. Could be in the area of, say, 4,000. This is fine when one would think that you'd like to use this high permeability material because by using high mu R or high permeability, the core will become smaller. Unfortunately, there are some problems that prevent us from doing that, and I'll go into it in a while. But before that, let me just state that a major problem that we have to face is the fact that all the ferromagnetic materials that we are familiar with, that we know, do have a saturation phenomenon. That is, if you look at the BH curve, it is pretty much straight line. The slope of this curve is this permeability. And once it gets to a certain magnetic field strength, H, it starts saturating. That is, B, the magnetic flux density, does not increase anymore. This poses a major problem because if this slope represents permeability, then in this case, when you reach saturation, the slope is very low, so consequently the permeability is very low, and so the inductance will drop. In fact, what will happen is that instead of having an inductor, you'll have just a piece of wire wounded on a core which is not behaving as a ferromagnetic material. So these are some of the constraints that one has to face when designing a power high-frequency inductor. Now, permeability, as I've said, is defined as a product of the initial or vacuum or air permeability, and this is the value of it, and these are the units, and times the relative permeability, which for ferrite will be in this range, unless you do some specific things to reduce it, and we'll talk about it. Now, B, the magnetic flux density, will be mu times H, where H, the magnetic field, is N times I. Now, as I've already mentioned before, contrary to the intuition, there is a problem using high mu material, because if mu is high, and here the slope is very steep, then very quickly, for a given H, which is N times I, the core will go into saturation. On the other hand, if mu is moderate, like here, still you are in the safe zone. So there is a point in lowering the mu as the power goes on, and we'll discuss it a little bit later in detail. Now, in order to reduce the permeability, there are two ways to go, among others maybe. One is to introduce a gap in the magnetic path. That is an air gap. There's a void here in which there is no ferromagnetic material. Okay, the windings are going this way on the ferromagnetic material. Now, as a result, you are sort of diluting the permeability of the magnetic core with the permeability of air, and you can then adjust it to whatever you want. We'll discuss it in a minute. Another way is to use a distributed air gap. Well, it may not be air, but what you do is actually put some inert non-ferromagnetic material inside the material. I mean, it's part of it, so that in fact you do have sort of a gap which is distributed throughout. Now, the advantage of this distributed air gap is that there is no discrete gap as here, which is very good because an air gap is rather troublesome, and I'll show it in a minute. Before that, let me just say that normally this air gap is small. It could be like 1 millimeter or 0.1 millimeter, when the magnetic path could be like 10. So normally the gap is smaller than the magnetic path, and therefore we sort of approximate, say LE is LE is the path within the ferromagnetic material. We just use the whole path. Now, about the gap. As I've said, the gap is troublesome. There are two major problems with it. Number one, that it radiates magnetic energy or magnetic field, which causes interferences, which is very bad, and we have somehow to protect against them, because the equipment may not pass the radiation standards. Another problem is that if there is a winding, like I'm showing here sort of a cross-section of a winding here, near the gap, the strong magnetic field, which is sort of surrounding this gap, will cause a crowding of the current. That is, if you have a wire which carries on charges. If you impose a magnetic field on it, then the current will sort of concentrate in one area. So what happens is that rather than having this diameter of a wire, you have actually a smaller wire. So the resistance will be higher, and of course, for a given current, the temperature rise will be higher because of the thermal losses. So these are really the problem with the gap, and usually you'd like to move the windings from the gap and not to put them on it because of the reasons that I've just mentioned. Now, if we have any inductance or inductor with a gap, and I've said we're using this calculation, and taking into account that the flux density, B, magnetic flux density, is the same both for the magnetic material and for the air. I am sort of neglecting the fact that some of the lines of phi is the magnetic flux, is sort of escaping here. To effect approximation, B here and B here are the same. These are the same lines of flux. So consequently, you can express as the magnetic field in the gap and magnetic field in the magnetic material as B over their respective permeability. Without going into too much mathematical details, you can sort of get an expression for H of the complete assembly, that is mu E is now the mu of the composite element, that is the ferromagnetic material plus the gap, and then you can use some other relationship that, let me not go into it. Whoever is interested, just stop the slide and look at it carefully. The very important result is given here, and that is that if Le, that is the magnetic path in the ferrite, is much smaller than, divided by the path through the gap, is smaller than the mu r of the ferromagnetic material, then you can use this expression. Let me first clarify. This will be the mu r of the, say, ferrite, to be 4000. And if Le over Lg is, say, 60, that is, the gap length is 60 times smaller than the ferromagnetic path, then, the magnetic path is the ferromagnetic material, then the mu of the assembly will be Le over Lg. So if, for example, Le is 100 millimeters and Lg is 1, then mu r will be 100, much smaller than the 4000 of the original ferrite. And these are the numbers that we may use for high power application. Now, looking now at the relationship between the voltage imposed on the inductor, the current going in, and the magnetic flux, these are the state equations here. And again, I'm not going into much detail of the maths here, simple sort of manipulation. We end up with an expression for the inductance of the core. The inductance will be n squared, that is the number of turns squared, times the cross-section area. Cross-section area means that if you sort of cut the core and look at the area here, this is AE. This we call the winding area, which we'll use later on. But now we concentrate on the cross-section area. Mu is the mu, actually it should be mu E, that is mu of the assembly, and LE is the magnetic path. This is the length of the magnetic path. So we find out that the inductance is a function of n squared, the cross-section area, and the length as well as mu. Higher the mu, the larger the L. Fine. This is what we said before. We like to have a material with very high mu, so that if mu will be high, we can use fewer terms, which looks on the surface very nice, but as I've said before, this is not the case, and we have to be very careful about it. So let me just reiterate here that if you have now two windings on the same core, L1 and L2, the inductance that you'll see looking at one winding or another is a function of N1 over N2 square, and not just N1 over N2, which many times people are mistaken about. Now, if we go now to the actual design of an inductor, what are the considerations we have to take into account? Number one is the saturation problem. We don't want to move into here. We like to stay, say, here as high as we can, because we want to be able to work at high magnetic field, that is high NI, high currents. Then we have thermal considerations. We have to make sure that the core, the assembly, the inductor, will not increase, the temperature will not increase beyond a critical point in which the material will deteriorate, not to mention the fact that we are losing power and therefore the efficiency might go down. Another concern is, of course, size. We want the size to be as small as possible. Now, of course, if, say, we use a very large core, temperature rise may be very small. That is, we use big cores, heavy wire, and temperature rise will be, just say for the sake of argument here, 1 degree centigrade. That's very poor, because it means that it's a waste of material. The core could be much, much smaller with a moderate temperature rise of, say, 10 degrees, which is fine. 20 degrees may also be okay in many applications. So how do we approach the problem of design? We start with the requirement of saturation limit. We set up the B maximum that we allow. That is, we don't want to go beyond it. And then, using again the state space equations, the relating L, and the current and the flux, the magnetic flux, to the voltage, and then doing some manipulation, we extract an expression for AE. This is the cross-section area of the core, and the number of turns. Now, the number of terms depend on a number of parameters. Number one, the window that is given to us, winding window. The current, that is, the heavier the current, the heavier the wire we need, the larger diameter of a wire we need. A measure is J, the current density that we allow in the wire, the ampere per meter square, say. A good number is 4.5 ampere per millimeter square, but it depends on the application. Now, if you use higher current per millimeter, the wire will get hotter. If you use much smaller, lower current, it'll be okay, but again, it's a waste. Now, you can see that, in fact, the area, winding area depend on the RMS and J, and this brings us to expression for the N as a function of J, IRMS, winding area, and another factor, which is called the field factor. And this field factor stands for the fact that when you have a winding here, the cross section of a winding, there is some dead space that you are not using in between the wires. So the field factor will be 1 if ideally you could have filled all the window, but this is not the case, of course. So therefore K practically will be a smaller number. It might be something like 0.7, 0.5, depending on how you wind it, machine you use, the cross section of the wire, whether it's round or maybe square. So this is a factor that you have to take into account. With expression for AE, expression for N, and since this is a function of the window area, and this is here the cross-section area, we come up with the very important equation. Very important, it's a basic design equation of what we call the area product equation. What is the area product? That's the product of the area of the cross-section area, times the window area. It's kind of strange. I mean, it's not the volume, because we're talking about a core, we're talking about the window here, and then the cross section here. This is the winding area. So the product of these two is this parameter AP. However, it does give us a sort of measure of the size, because obviously the larger the area, say the larger the number, the bigger the core will be. Now, what is very important about the equation is the fact that it has here all of these parameters are known. We know what is the inductance we need, we know what is the peak current. In a specific application, the inductor current will be, say, like this. This will be in a switch mode converter. This is the peak number, the peak value. This is the inductor current. Now, the RMS is this value here. It's not average. I'm talking about RMS, which is IRMS is, of course, 1 over T, square root of 1 of I L square dt, and this is the integral of this over the period T. Now, if we look at this, and then the equation contains B maximum, which we have set, the J, and the fill factor. If you look at the equation, you see that there is here a product here at the denominator, which is sort of is very close to the Li square expression. And since energy stored in a core is Li square over 2, we see here that the size in terms of AP of a core will be a function of the energy stored in it. That is, if you have to store a lot of energy in the core, if I is high and Li square over 2 is a large number, there's no escape. You need a bigger core. Otherwise, you'll either violate the saturation limits you've set or the J, that is how much current you allow in the winding. It's interesting to know that AE and AW, that is the cross-section area and the window area, are sort of interchangeable. That is, you can use a core with a small AE if you compensate it by a larger area that is more windings. We assume, of course, that we are filling all the area here with the winding, which may not be always the case, but we are trying to maximize the core by doing that. So this is a very, very important equation. With this equation, one can actually design a core in a straightforward and one-way direction rather than iteration, which other methods are using. So how do we approach the core design in the case of the gapped core? We first of all calculate AP. We know all the parameters, the peak current, etc., that we want, the inductance that we need, and we can come up with an AP. Then we go to a catalog of a core manufacturer and select a core. Well, there are many shapes. This is something we have to decide about. I'm not going into it here. And you choose a core that has an AP of the catalog, which is higher than AP that you need. Otherwise, the core will go into saturation, or the current in the inductor, in the conductors, in the wires will be higher than you wanted them to be. Now, once you do this, you calculate everything, and then you may wish to sort of go back and do some iteration, select another core. But basically, once you got a core with an AP which is larger, that's fine. It's going to be okay. Then you calculate mu that you need. To do so, you use the equation for N, which I had before, and once you know N, then, and you know L, that is the inductance that you need, you can calculate mu E that you need. Well, if you know mu E, you know now the dimension of the core, you know what is the magnetic length or magnetic path of it, then you can calculate what is Lg. Well, sometimes you can do it experimentally. You can sort of file down the core until the inductance reaches L. So this is really a straightforward procedure once you are using this AP product equation. Let me now talk about cores, and again I'm talking about inductor cores with a gap, and this is what we talked about up to now, as opposed of course to a transformer which does not have a gap. There is no need. In fact, a gap in a transformer is sort of deteriorating its behavior. By the way, there is an element for flyback converters that sometimes is referred to as a transformer. It is not a transformer, it is a coupled inductor. That is an inductor with two windings, and it does have a gap. So gaps are coming in various shapes. There's few examples here. There are many shapes and forms, and it's a story by itself, which is really outside the scope of this presentation. And here just an example of a, I guess it's an E-core, or actually it's a D-core. This is the bobbin. Here are the two parts of the cord, which kind of go inside, and these clips are closing on it, and then you put the winding on it, and here is a winded element. Of course, the gap is one place to put it here, or you can put it here, here, also, or in 3 places. Normally, it's done here, and you can buy cores already shaped with a gap. So when you close the two together, there is a air gap between the core. Now, let me start with the distributed gap core. As I said, it has many advantages. Material is a little bit different than ferrite. In fact, somewhat inferior to the ferrite in general, but as I've said, it has the major advantage of not having a gap, which is radiating and the problem of current crowding, etc. Now, a important parameter of distributed gapped core is A sub L, and it is Henry per turn. That is the inductance you get per turn, and many times it is quoted as inductance over 1,000 turns. Well, some manufacturers do this or that. Now, if it is Henry per turn, then the inductance you will get with a given core will be N squared, we talked about it, times AL. Now, here's an example from a sort of application note of a manufacturer. This is magnetics in this case, which give the expression for N. This is the expression we found before, except that the actual mu is mu0 is given here. Okay, this is this 4 pi over 10 to the 8. This is mu0, and states that the AL is L1000. This is L1000 is AL. That is that the number is for 1,000 turns. So therefore, since again the inductance is a function of N square, to find out what is the inductance of a given core when AL is per 1,000, you have to divide it by 10 to the 6, which is, of course, 10,000 squared. Now, if we look up at say, the magnetics catalog again, we see cores, the number of cores with different permeabilities, that is 60, 125. These are the parameters of the core, say electrical parameters or relevant electrical parameters. This is the window area, the cross-section area, the path, magnetic path length. You have also the volume, which you'll see is important, weight, which is for information, and area product. This is something that we've seen is important. And also the mechanical dimension are given here. So how do we go about choosing a given core from the thousands or maybe 10,000s of cores which are available? So let's see some of the information that we'll have to use in the procedure of selection. One curve is very important, is this curve, which shows how the permeability goes down as the DC magnetization of the core increases. That is, when I feed the current to the wire, here's the current, there's an average current. This is the DC value of the current. It's the average current. And if the average current is high, I'm moving on this curve from, say, here, maybe to here. And of course, as I move up, first of all, I may hit the saturation, but even before that, as you can see, the slope here is changing. That is, mu is changing. And if mu is changing, the inductance will be changing. And this is exactly what these curves are shown, and they are shown for different permeabilities. That is, if the core has 125 permeabilities, this is set. You can't change it. I mean, you not put any gap in it, that's it. So if you choose a core with 125, then pretty quickly, I'd say, the core will lose its permeability. Why is that? Because the mu is high, okay? Higher mu, faster you go into saturation. By the way, the dimension here, I mean, the units here are Ørsted, which here the relationship to ampere meter. So this is an important curve we're going to use, and there is another important piece of information, and that is the losses, the core losses. Now, as you have a variation of the current, inductor current, B will change. That is, you move along on the hysteresis curve like this, because you're changing the current, and B, which is here, this is B, and this is H, this is the delta B. Oh, sorry, delta B. So magnetic losses are a function of delta B because of the energy that has to be put into the core for actually magnetization, and it has to one has to take into account that this is a function of frequency, because the higher the frequency, more times you are sort of changing the magnetic direction, and therefore the losses will be higher. So the curve we have here is, on the one hand, the flux density. This is not flux density, by the way. This is delta B. That is wrongly labeled here. And loss. Loss in terms of milliwatt per centimeter to the third. That is milliwatt to the volume. Each centimeter to the third is this will dissipate that much milliwatts. So here we have a number of frequencies, like this will be 500, this will be 25. 25, of course, for a given flux density, 25 is much lower. Well, 500 is sort of off scale here. And in the design, you have to decide how much thermal energy you can tolerate, how much power you are willing to sort of lose, and in terms of the power loss of the magnetic losses. And it depends on the application. A good number will be 100 milliwatt per centimeter third cube. In some applications it will be lower, some applications you can choose higher, but this is a good number to take into account. Now, this curve actually was generated by operating the core around the zero region. In fact, if you move to a point where you have some DC superimposed, that is, you move like this back and forth, losses may be a little bit higher. There is not too much information about it. One should be aware. Now to the point of temperature rise. There is an experimental equation that was kind of was found experimentally, which is shown here. And what it shows is that you can sort of estimate the temperature rise by taking into account the total power loss. This will be the wire loss, that is the resistance of the wire, times I square RMS of the current flowing through the wire. So this will be the resistance wire. And then you have to add to it the magnetic losses, which we just spoke about, and divide it by the surface area. Why is that? Because the surface area of the core, here is the core, which is a wound surface, total surface area, is the way that this core dissipates the energy, or the thermal energy, or the heat to the air. And this ratio has to be raised to the power of 0.833. This is again was found experimentally, which is a sort of a first order approximation of temperature rise. So for each design, one has to decide what is the temperature rise that he allows, and once the core is designed, go back and check if the temperature rise is okay. Another piece of information is what's called the Hama curve. Again, starting with the basic equation, which I will not go into the fine details here, you end up with a relationship which sort of relates the magnetic flux and magnetic field to the energy and volume of the core. And based on this, Hama, which is a person, scientist, suggested this type of a curve, which is kind of very interesting. Here is the magnetic field, N times I, and here is Li squared over VE, energy per volume. And this curve is for various gaps. It was originally calculated for gaps, but basically this is 1 over mu, because here it shows, it's hard to see, this is the ratio of the length, and this is 1 over mu. So what we see here is the very important information that as you need more energy to store, or the current goes out and you need a higher current, or if you wish, as you go up with the energy, you will have to use smaller and smaller mu's. That is, here the mu is 1 over 0.002, which is 500, while here, say, take a simple number, it's, I'm sorry, it's hard to see even for me, that I'm assuming that this is, let's see, here, this will be 20. So the higher the energy, the larger the volume that you need, and the lower the mu that you'd like to use in order to utilize the core properly. Based on this Hama curve, manufacturers are offering this curve, which is sort of a way of presenting this Hama curve. Here we have Li squared, and here we have actually already catalog numbers of cores, which embed in them, of course, the dimensions. So once you know Li, say here, this is the inductance that you need and the current square that you expect. It should be the peak current. You hit up the point here, and what you see here, that as you go up with energy, mu is going down, and you can just choose the core. You choose, this is the sort of the family of the core, but you have to use the proper mu. Each core is coming with different permeabilities. You've seen it before. So this is rather straightforward. You know L, you know the current, you calculate Li squared, you go to this curve, and you pick up the family of the core and the mu that you need. Once you do this, after you calculate Li, you look at the curve, you select the core, you calculate the number of turns you need from the given AL of the core and the inductance that you know. You check L minimum, that is this curve with the DC effects on it. You calculate losses, temperature rise, and you see if it's okay with you. If not, you just go and take a larger core. This is the only remedy if it's too tight. And you do this until you find the optimum core for your application. This brings me to the end of this presentation. I thank you very much for the attention. I hope it'll be useful to you. Thank you.